This video is going to be an introduction to exponential functions. So I have a general exponential function written here in function notation, f of t equals a b to the t. So just as a side note, this is the same thing as if you saw y equals a b to the x. It's just in function notation instead. So a is our initial value. B is our growth factor, and t is our time. This is exponential functions in general. So it can model exponential growth or exponential decay. So if it's exponential growth, our growth factor, b, is going to be greater than 1. If it's exponential decay, b is going to be between 0 and 1, 1/2, 1/3, 2/3, 3/4, something like that. So let's take a look at two different examples. Exponential growth would be 4 times 3 to the x power. So my initial value is 4. And my growth factor is 3. So A would be 4, B would be 3. And this would be growing or getting bigger. So for example, if I go to my calculator and I type in 4 times 3 to the first, I get 12. 4 times 3 to the second, I get 36. 4 times 3 to the third, I get 108. So this is 12, 36, 108, and so on. It's growing by 3 or multiplying by 3 every time. Exponential decay would be something like 4 times 1/2 to the x power. So the same thing happening here. My 4 is my initial value, and the 1/2 is my decay factor. So A would be 4, B would be 1/2. And if I go back to my calculator, I can do the same thing here. I'm going to put in 0.5 instead of 1/2, but 4 times 0.5 to the first is 2. 4 times 0.5 to the second is 1. 4 times 0.5 to the third is 0.5. So 2, 1, 0.5, and it would continue. Notice how it's getting smaller. It's dividing by 2 or multiplying by 1/2 every single time. So this is our general exponential equation. Y equals ab to the x, or f of t equals a times b to the t. There is another way, or there actually are a few ways, but there's one other way that we are going to look at exponential functions. So exponential functions can also sometimes be written in this form, which you may have seen as y equals a1 plus r to the t. I have it written as a equals p, 1 plus or minus r to the t, but it's the same idea. So p is my initial value, just like a was. R is my growth rate, not a factor this time. And it's very important that we understand the difference. And t is still my time. So if I write y equals a b to the x, or we could even change this b to the t. I want to compare my two. My initial value is my a or my p. My exponent is t. So this piece here is related to that piece. And that's what this says down here. B is equal to 1 plus, or of course, minus r. So if it is growth, it's going to be 1 plus R. If it is decay, it's going to be 1 minus R. B is my growth factor, and R is my growth rate. And rate is usually given as a percentage, but put in the formula as a decimal. So we're just going to look at 2 quick examples, and then that'll be it. So here's my growth and my decay example. So remember, my initial value is still in the front of my parentheses. This 0.03 is my rate. So my A is 40, my rate is 0.03. If I were to combine this together, I would get 40, 1.03 to the x. And in that case, my rate would be my factor, sorry, would be 1.03. Notice how B is larger than 1, so it's growth. And there's a plus, so that tells me it's growth. For decay, still my initial value. This is my rate, but notice how this is a minus, so it's going to be decay. My initial value, or my A, is 40. My rate is 0.03. But if I combine these 2 pieces together, if you're unsure, you could, of course, use your calculator. Notice how my decimal changed between A and B, or between growth and decay. Oops, still on the highlighter. My B is 0.7. B is between 0 and 1, so it is decay. So these 2 different equations are related to each other, but it's very important that we understand the difference between growth factor and growth rate. Rate is a decimal before it's been added or subtracted to 1. My factor is a number after your rate has been added or subtracted from 1. So B is equal to 1 plus or minus R.